In this video, we are going to learn how to build classification trees for predictive purposes. Assume now that we have another firm where an employee has come up with an invention and is trying to decide if she wants to patent her invention as opposed to keeping that as a trade secret. Let's suppose that her company is willing and able to commit to the expenses associated with patenting if and only if they have a reasonable assurance that if submitted, the application will become granted within 3 years after the submission. Let's assume that otherwise the firm is not ready to pursue a patent and would instead be inclined towards keeping the invention as a trade secret. So to decide whether to patent versus to keep as a trade secret, the company has to predict whether or not the patent application, if submitted to the United States Patent and Trademark Office, will turn into a granted patent within 3 years. You can notice that the problem we have here is inherently different from the one that we discussed earlier. And it's different in that here the variable we want to predict takes two values only, and those have no numerical meaning in them. Those two values are granted and pending within 3 years after submission. Now remember that situations such as this present a classification, not a regression problem. Regression problem, as we discussed, deals with the prediction of quantitative outcome variables. Here we do not have a quantitative outcome variable. We have a categorical outcome variable. We have a classification problem. Now there are a number of different modeling strategies to approach a classification problem, and here we will discuss one such strategy, the classification tree. Classification tree is a decision tree made up of nodes where questions are asked and other nodes where decisions are made. On a high level, at each blue node, a particular question is being asked about one of the independent variables. Now, if based on the data, the answer to that question is affirmative, then one visually moves to the left branch, at the end of which either there is a new question being asked about one of the independent variables, or that branch pretty much terminates. The terminal nodes, in other words, the nodes that appear in green in this diagram, do not pose new questions. Instead, they assign classifications, and those classifications are based on the values of the dependent variable for all the observations that fall into that terminal node. The number of terminal nodes determines the size of the tree. So in our hypothetical example that you see, the size of the tree is 4 simply because there are 4 terminal nodes. Classification trees are part of the classification and regression tree CART approach, which is an umbrella term incorporating classification trees that offer solutions to classification problems, as well as regression trees that are pertinent to regression problems. A good way to understand how to use classification trees is to continue with our example, where a firm was trying to classify a patent document with given characteristics to either granted or pending status 3 years after the submission to the patenting office. The data for this example, which is for a different firm than what we discussed in the regression video, is provided as an Excel file. And just like before, let us randomly split the data into two subsets, the training and validation sets. The training set will consist of 913 patent documents, and the validation set will consist of 5 patent documents. And just like in the regression example, we will develop our predictive approach using only data in the training set. Notice that about 83% of patents in the training set are granted within 3 years, and the rest are pending at the end of the 3 years. The validation set will be used to evaluate the accuracy of our predictive model. how do we build classification trees? Let's say we are standing at the root node, that is at the top node of the tree. The tree is built, or as we like to say, it's grown from top to bottom based on the so-called recursive partitioning approach. And that is an iterative approach to grow classification and regression trees, and is carried out in a number of statistical software, including R. We won't be going into the technical details of the approach here, but in a nutshell, what the method does, it splits the space of independent variables, also known as the predictor space, using only horizontal and vertical splits. And this is done in a way that renders each resulting subset of data as homogeneous as possible in terms of the distribution of the dependent variable. So currently we are standing at the root node and no branches have been grown yet. To determine the particular branches that would grow out from the root node, notice that a number of various splits are experimentally considered at that node, and the split that renders the highest improvement in homogeneity is carried out at the root node. In fact, this process repeats itself at each node to determine if a split should take place at that node, and if so, then using which variable and which split. One thing to remember is that typically classification and regression trees are grown using available training data to a size that probably is greater than what an effective tree size should be. But here's the trick. When we overgrow the tree, we do not stop there. Instead, trees are subsequently shortened, or in the parlance of trees, we like to say they are pruned. And this is done to eliminate the terminal nodes that emerged from splits which did not add much value in improving the homogeneity. More technically speaking, pruning starts from the bottom of the tree, and from there we sequentially eliminate the terminal nodes that we know are emerging from splits that do not significantly improve the homogeneity during growing of the tree. You are already noticing that pruning is a bottom-up approach, since we start from the bottom of the tree and we move up, and it turns out that the pruning terminates once we know that all of the remaining terminal nodes emerged from splits that significantly improved the homogeneity when they were carried out during growing of the tree. Notice that there are several formal mathematical measures to evaluate how homogeneous a particular partition is, and in the classification context, the classification deviance as well as the so-called Gini index are among them.